So, welcome you all to this discussion on facilitating ethical AI systems in financial service industry. It's basically responsible lending and beyond. So, this will be the brief agenda of our presentation. So, we'll walk you through what a key introduction to ML models. Then we'll assess what is the market size of AI in fintech and what are the capability stacks in banking. Then we'll do a sneak peek into what ML model does and why do we need fair ML models in place. And then, of course, we'll walk you through what are certain frameworks of developing unbiased fair models and what are the challenges and opportunities for fairness research. And then we'll conclude with the key takeaways from the exercise. So, right. So, essentially, financial institutions are increasingly capitalizing on cutting-edge technologies, which is facilitated by integration of ML methodologies. And because of large-scale automation capabilities and cost cuttings have made ML algorithms a lot more prospective and attractive for personal and professional finance, corporate finance applications. But however, of course, this represents novel, possibilities to reimagine customer engagement. At the same time, if not adequately designed, it can be mismanaged and can cause severe harms. So it is imperative to ensure that any AI and ML model that is used in decision making follow principles of fairness, ethics, accountability, explainability, privacy, security, and governance. And of course, how can you ensure that you can ensure only by encoding precise statements of ethical standards into our modeling designs so as to make responsible decisions. So with that notion, we'll just walk you through what is the market size of AI in fintech. So AI in fintech was valued at close to 9 billion in 2021. And then, of course, since then it has grown exponentially to 11.35 billion in 2023, and it is expected to grow up to 14.41 billion in 2024, with an expected CAGR of 27.1%. And the AI in fintech's market size is still expected to see further exponential growth, and it's expected to grow up to 39 billion in 2028. So, what drives this? So, of course, profitability, right? There are three key aspects to this. One is personalization at scale, then of course omni-channel presence and the speed and innovation at which all of these developments happen. So when it comes to reimagining engagement, there are a lot of intelligent products and tools and experiences for customers as well as employees. So you can think of all the apps which you use, right? At apps or the mobile apps or all the web-based platforms which we use, even the UPI. So and of course, beyond bank channels such as our ATMs and one-to-one representatives to tailor, personal preferences. So these are the kind of engagements which have kind of reimagined customer engagement with the finance industry. And what has ensured all of this? Of course, analytics in certain areas, right? So basically, we use behavioral analytics for predicting for customer acquisitions, credit reasoning, monitoring and collections, retention of retaining customers, cross-selling and upselling, basically enhanced products, servicing and engagement. So these are the key AI capabilities which we use in our banking space. So for, like I already said, for behavioral analytics, we leverage predictive models. For NLP is leverage for sentiment analysis, so on and so forth. Virtual bots and agents are used for 24/7 customer assistance. And of course, computer vision is used for assessing check frauds, then multi-factor authentication, and blockchain, of course, is the key behind Bitcoin, Ethereum, decentralized services. So these are the key aspects of and the capability stack of ML in our banking space. So of course, with the widespread adoption of AI in our daily life, we are at the dawn of a fourth industrial revolution, accelerating more towards an algorithmic society. And of course, there are key benefits to it. The reason particularly being machines, unlike humans, does not get tired, and we have capabilities which are actually unmanageable by by humans basically. But of course, AI's algorithms suffer from opacity. It is difficult to get into what is the internal mechanism of any ML algorithm. So because of these problems, it is difficult to enter certain important decisions that a system makes, which itself cannot explain, right? And there are several key examples which are in place, which will kind of make you understand where key ML methods have gone wrong. So one of them is basically Compass. So basically, this is a US code software which kind of predicts what is the probability a prisoner is going to commit a further crime. And it was found out that it was pretty much skewed against African Americans as compared to Caucasian offenders. So this was in 2016, and there are and there are beauty pageants which was skewed against the dark-skinned contestants in 2018. Then advertisements promoting STEM fields to was biased for men against women. The fourth aspect is basically facial recognition systems kind of make an argument that Asians blink compared to other Western population. And this was in 2019 when Apple and Goldman Sachs came up with an Apple card. It was accused of giving lower credit limit for female employees. So these are the kind of examples which have popped up in the last 5 years, and of course that has stemmed a lot more focus into explainability and fairness in almost any domain, not just to banking industry. So while the term is relatively new, the problem of fairness and explainability has started in 1970s. So it's a 50-year-old what's called dimension, but the pace of progress towards resolving such problems have slowed down because of reaching an inflection point where you made spectacular advancements in developing highly discriminating models. But as you can see, the Google Trends research since 2016 that has taken a cliff post 2016. So most of the literature in this field has actually come in the past 7 years. So yeah, which is something which we'll focus on. So, and of course, why do we need fair ML? There are 4 key reasons. One is the need to justify, because there are already a lot of instances where we have pretty much established there are severe discrimination or bias against minority classes. And second thing is, of course, need to control. So understanding more about the behavior would provide greater visibility over what are the unknown vulnerabilities and helps us rapidly identify and correct those errors. And what is the need to improve? So users know why the system has outputted you provide certain outputs. So they will also know how to make it smarter. So this could be a foundation for ongoing iterations and improvement between a human and a machine. The fourth is need to discover. So asking for fairness is helpful to learn about new facts, gather information, also to develop more knowledge on these systems. So these are the 4 key reasons why we need to adopt for fair ML. And how do you develop these fair ML models? So basically it's a conglomeration of 3 aspects, right? So it's a feedback loop. It starts with data, algorithms, and to user experiences. So fairness for a layman is basically an absence of any prejudice or favoritism towards an individual or a group based on their inherent or acquired characteristics. And it stems from data all the way to algorithm to user experience and back to data. So because all of our models are data driven. So if there are inherent biases in the data, that itself will bias these algorithms on which are already tuned on that, right? And when it comes to algorithms, that even if the data is not biased, algorithm can itself has their own bias because of the kind of frameworks which you resort to. So basically, it may depend upon certain regularization functions, optimization functions, so on and so forth. And then it goes to user experiences. So let's say we have an algorithmic bias where we are highly skewed towards producing certain results, where the consumers are expected to respond when you do a normal search. They respond to most of the aspects, understanding what are the bottom of the web search, and then that comes back as a feedback loop as data, and then the process goes on. So of course there are 3 ways in which we can pretty much develop fair models, right? So of course we can sort out issues with data, algorithms, or user experiences. So I'll walk you through what are the common problems with all of these. So basically, first with data. First we'll start with measurement. So measurement basically resorts to how you measure certain attributes when you curate your data, right? So a classic example is like what I already told. So in the Compass experiment, which was Compass product which was launched in US courts, one of the key variables used were felony committed by fellow community. So basically, which itself is a mismanaged proxy, because in US, let's say minority communities are policed very strictly. So the probability of them getting arrested was slightly higher than when you compare a native person, and that in itself actually kind of created a bias in developing a highly predicting model stating that someone from an African American background is more likely to commit felony once he's released. So second thing is sampling bias. Sampling bias, of course, when you don't have a diversity of subgroups within your sample, so that will kind of create a bias on that. Third thing is Simpson's paradox. So Simpson's paradox basically an aggregation bias when you aggregate your data. A classic example happened in 2016. So what happened is in UC Berkeley, a gender bias suit was filed for not having enough female students in their graduate programs. But however, when they evaluated the exercise, it was figured out that all of these female candidates applying for one department where the intake was fairly low, in fact, the female admissions was much higher than men. So these kind of biases can only be picked out if you do enough causal exercises. So these are the kind of biases which actually help comes up in data. Algorithms, like of course, it comes from design choices. So it might depend upon the regularization or optimization functions which you resort to, and on what all benchmarks where you evaluate the strength of the model. So those comes to algorithms. What are user experiences? Basically historical bias and social bias. So there is a certain setup in which a society has been formed, and they kind of tend to, so let's say if you do a normal Google search for a CEO, more likely you're bound to see a white, a white person at 85% of the times, because that's the way the society has been. I mean, the data has been, we have got the data for the past few years. So is it discrimination? Strictly saying no. But having said that, you don't get a chance to have a black colored woman photo emerging even if you train the algorithm, unless and until you have got that, a diverse set of groups. And third thing is, social bias. So these kind of aspects comes when you do a movie rating. So you didn't like the movie. Let's say the movie rating is pretty poor, by the way, but most of the peers, or if you see the average ratings, they are pretty much high. So you tend to skew your response to what you don't want to do, and that kind of picked up by the algorithm and in terms tunes the algorithm in such a way, creating bias models. So these are the key ways in which models get biased. I'll also walk you through what is discrimination, because they go hand in hand. So bias actually, in terms of literature, comes from data collection, sampling and measurement, whereas discrimination comes from prejudice and stereotyping based on sensitive attributes. So there are two ways you can explain. One is explainable discrimination, other one is unexplainable discrimination. So when it comes to explaining discrimination, the treatment and outcome of both groups can be explained by some attributes, like what is talked about the UC Berkeley experiment. Whereas sometimes it becomes very difficult to give an explanation, and that is where things are going wrong. That's unexplainable discrimination. And how do they happen? It can be systemic or statistical. Systemic means there are policies, customs or behaviors that are part of our culture. So that may perpetuate discrimination against certain group of individuals. So let's say when you go to a hiring program, most likely you are bound to see people people sharing common hobbies or common traits getting hired by the interviewers. So that's the kind of discrimination which are systemic. And statistical, basically what we do average group statistics to estimate what is the belonging of the particular person into a group. So these are key aspects in this area. And now we go through what are the formal definitions of algorithmic fairness. So in the 50-year literature of algorithmic fairness, we have we have come with close to 8 formal definitions of fairness. And one of the most common ones are equalized odds. So equalized odds states that what is the probability of person in a positive class being correctly assigned a positive outcome, and the probability of person in a negative class being incorrectly assigned a positive outcome. Both of them should be same for both protected and unprotected class. So what it means, so you have A as a sensitive attribute, let's say in this case a male or a female. So the probability that y hat is equal to 1 given A is equal to 0 and y is equal to y should be equal to probability y hat equal to 1 given A is equal to 1 and y is equal to y. So that's the foremost definition. And of course second thing is equal opportunity. Equal opportunity definition states that the protected and unprotected group should have equal true positive rates. So which states again the probability y hat is equal to 1 given A equal to 0 and y equal to 1 should be equal to probability y hat equal to 1 given A equal to 1 and y equal to 1. Third is demographic parity or statistical parity per se. So it states what the likelihood of a positive outcome should be same regardless of whether the person is in the protected or unprotected group. Which means the probability y hat given A equal to 0 should be equal to probability y hat given A equal to 1. And then there are more generic definitions like fairness to awareness. So an algorithm is fair if it gives similar predictions to similar individuals, masking other attributes. And fairness to unawareness. So an algorithm is fair as long as any protected attributes say are not explicitly used in decision making process. Treatment equality. Treatment equality is defined as a ratio of false positive rate to false negative rate to false positive rate for both protected and unprotected groups. Now we have test fairness, so which states that if the predicted probability of a person is, let's say, is S, then the people in both protected and unprotected groups should have equal probability of correctly belonging to a positive class. So let's say someone has a score S and he belongs to R is equal to B and R is equal to W, his probability Y equal to 1 should remain same. And the last one is counterfactual fairness. It's the intuition that addition towards an individual, if he's same in both an actual and counterfactual world, where the individual belong to different demographic groups. So irrespective of the race or the sensitive attributes, it's expected that an individual receives same treatment in the same and the counterfactual world. So these are the key 8 definitions which have emerged from all the surveys, and of course then that's how we start our fair machine learning process. So like I already said, there are 3 ways to do fair machine learning. One is data, one is algorithms, and one is research experience, right? So it starts from pre-processing. So what pre-processing does? Pre-processing try to transform the data so that any underlying discrimination can be removed. A classic example would be to unbias the data. And in processing techniques, what it does, it tries to modify all of our state-of-art ML algorithms by introducing certain objective functions or constraints so that they develop fair results. So there are some articles which have come under this arena in the past few years, and they are fair classification, fair regression, fair PCA, fair clustering, and fair NLP. We'll touch base on one of these techniques in the due course. And post-processing is basically once you train the model, you have the output. Now you put a threshold in such a way that the labels kind of have equal probabilities across class. So basically in a credit decisioning system, let's say you have a score and you kind of see an bias across groups, you kind of wave the threshold in such a way you get equal contribution across classes. So that's the idea. So this is pretty much manual in place actually. There are no standard techniques. So like I already said, how do you unbias the data? So every data set is a result of several design choices that is made by the data curator. So in order to mitigate any of these effects, it is important to have a supporting document that kind of reports the data creation method, the characteristics, the motivations, and the skews. Causal models and graphs can also be used to detect direct discrimination in data. And also its prevention technique can be leveraged. And other pre-processing techniques like preferential sampling to ensure you have a diverse set of groups, or disparate impact removal, which will have a sensitive group having a lot more attention in the training data. So all of this can be done to remove all these biases. So these are pretty generic aspects when it comes to data. Now we'll go to fair PCA. So which is an in-processing technique, which is an in-processing technique that is used to ensure that there is a equal contribution for any class that you train upon. So that's the idea. So if you see in the figure, right? So what they have done is they have tried to. So what PCA does? PCA is a standard dimensional reduction technique, right? So as you increase the number, so on your x-axis you got number of features, and your y-axis you got reconstruction error. So what reconstruction error is? So essentially, of course, you have a n-dimensional data and you want to reduce into d dimension, and of course, in doing so, do you get a right representative of both populations? So that's the whole idea. So if you see the pink graph, right? So basically male, if you generally see, tends to have a lower reconstruction error than female when they do a standard PCA process. And what they have done is they are trying to sample in such a way they have equal numbers of male and female candidates, and then they try to reweight the data and actually again did PC on top of that. So in the second graph, you can still see there is still a difference in the reconstruction error across both groups. So that is the motivation of the idea to do this exercise. So I'll give you a brief overview. What are the mathematical notation that goes for this? So we are given n-dimensional data having of matrix M of having real world values m cross n. So we'll refer to set and matrix interchangeably. The data consists of 2 subpopulations A and B, which are basically labeled. So in this case, we have binary sensitive attribute. So in this case, it could be male or female, right? We have AB, which is basically a concatenation of 2 metrics by row. We have the ith row of M as Mi and jth column of M as M superscript J. and ijth element as m of ij. So we denote Frobenius norm of matrix M as mf, and then term of the vector mi modulus mi. Right? So again given two matrix m and n of the same size, the Frobenius inner product of two matrices is defined as sigma ij, mij, nij. So this is the case. These are the key mathematical notations in this exercise. So what PCA does, given a matrix M having real world values m cross n, we find a matrix M hat of rank at most D, where D is less than or equal to n. That minimizes the reconstruction, which is basically M minus M hat. And we refer M hat as the optimal rank D approximation of M. So if M hat is a solution to the PCA problem, so then M hat is equal to M into W transpose, where W transpose is called as a projection matrix, and W transpose should be equal to an identity matrix. Right? And what fair PCA does, instead of asking for a single projection, instead of asking for two different projections, we are asking for a single projection which will have same reconstruction loss for two groups. That's the whole idea. For that, we'll walk you through a couple of more terminologies. One is reconstruction error. So given two matrices y and z are of same size, the reconstruction error of y with respect to z is basically y minus z square. You take the Frobenius, right? And what is the reconstruction loss? They're both different terms. So basically loss of yz would be, let's say y hat is optimal approximation of y, and z is another matrix of rank, at most D. So loss of y to z will be the loss of y minus z square minus y hat. Right? So if you see both of this, so this optimization will only improve if the loss of the group where the current representation is actually worse. So if you see two groups here, you have one. Take the first group. You have the first group is basically vertical and second group is horizontal, right? So any dimension if you do, so in the first group if you do a vertical dimension, it will perfectly embed into one dimension. Where on the other hand, if you do the other way around, on a horizontal dimension, it will fall equally, right? Any other dimension would actually cause equal errors for both A and B. So such is not a suitable solution for us. So that is why we actually go for reconstruction loss rather than reconstruction error. Same is the case with the second example. So you see a circle and you have a horizontal line. So you project them into horizontal line. So the second piece won't have an error, but for any other dimension, you're going to have an error for the first portion, right? So in doing so, any other projection will not add significant value by portraying them to a dimension other than that horizontal line. So we take care of all these, attributes and, formulate this methodology. So what are the constraints we have imposed in the exercise? So basically, given m data points with subgroups A and B, we find the problem of finding a fair PCA projection by optimizing minimizing the maximum losses. So basically, what is the loss? The loss of A given UA. So you have an A and B, you do a projection getting U, and UA will be the number of rows corresponding for A and B. Then you compute the loss of A comma UA and loss of B comma UB, and then you minimize the max loss. So that's the constraint which you have put this exercise. And if U is a solution to the fair PCA problem, then 1 by A loss UA is equal to 1 by B loss UB. So the idea is you have, equal losses for both groups. So this is how the algorithm works, right? So what is the input? You have two populations A and B. A having m1 rows and n columns, and B having m2 rows and n columns. So m1 plus m2 will be the total data set, and then D is the rank of the matrix which you are trying to optimize, and n is currently the rank, right? And what is U? U is the optimal approximation of A and B, and it will have m cross n with rank U less than or equal to D plus 1. So how do you do the optimal D approximation? We do singular value decomposition subjected to the following constraints. So what you do here, so basically you compute the errors for each of the matrix A and B. So A and B will have their optimal approximations. Then we have the losses that is defined by Z, which is basically 1 by M. M1 is the number of rows that is corresponding to A, and M2 is the number of rows corresponding to B. And we estimate the difference between, A hat square minus the Frobenius inner product of A transpose A and P. So that will give you the loss. And so basically it's an iterative weighting process where you go across and then you reach a point where you have an optimal projection. So and that is computed using singular value decomposition, and it returns a matrix A, B, and P star. So P star is a projection matrix which you are interested in. A and B will be your inputs. So and that kinds of ensures that you have equal losses. So that's the whole idea, and we've done this experiment, and as you can see here, On the left-hand side, we are doing the reconstruction error for 4 groups, and of course, the data is of 21 dimensions, and everything goes to 0. The reconstruction goes to 0 at full dimensions, right? And as you can see, there are slight deviations in terms of, let's say, there are 2 groups in here. One is higher education, one is lower education, and the error comes down as you have n dimensions. But if you go to fair loss, you can see the lower dimension groups having a higher loss compared to lower, and you have fair loss, which kind of ensures that you have, equal loss across any dimension, and it's up to the researcher to design where you want to make that cutoff, like how many dimensions you're interested in. So that kind of sums up this exercise what we have done actually. Yeah, but if you want, we have the codes, like just in case if you are interested and want to replicate. So of course, what are the challenges, right? So challenges, basically fairness itself has so many definitions. So synthesizing a universal definition itself is a challenge, and it's an exciting area to work upon. Second thing is equality to equity. So equality, which we have pretty much defined our protected class and control groups, but we pretty much know across groups what is opportunity given to people, so on and so forth. So that is one area which is still unexplored, and there is an exciting future work that's possible on those areas. And searching for unfairness, because fairness itself is pretty much problem centric. So the moment you understand what is the level of fairness you want to solve, you pretty much are able to identify what are the instances where you can solve this exercise. So inroads, like what we already talked about, Simpson's paradox. So these are areas which we needs unification, and and can have further outputs. And opportunities, like the research is still in very nascent stage. There are not enough papers in the past 10 years. So it's an exciting area, and there are a lot of areas that requires a lot more attention in these fields. So that are the kind of opportunities in this field. And conclusion, like I already spoke about it, it's a interdisciplinary research field in the AI ecosystem, and we have just given a comprehensive view of the field. We are just focused on who, where, why, when, and how we do all this to give a nascent idea of what is done in this field. So we see there's a lot of lack of formalism in the problem formulation, and there are clear unambiguous definitions when it comes to fairness. And it's very clear that there's a lot of attention devoted to developing discriminative ML models and letting other promising AI systems going unexplored. So can we conclude that there's a considerable effort required in future to tackle these challenges and open issues with fairness? So this is a very nascent approach. We still have not got lot of integrities are still pending. But yeah, that's pretty much about what we have done. Yeah, thank you.